We've gone through wires, both high frequency and low frequency, what they look like. We went through inductance, right? Partial inductance, I should say internal and partial, and high frequency effects through the internal inductance. We went through resistors, capacitors, and inductors, what they look like at low frequency and high frequency, and things to be concerned about. Anybody have any questions about any problems, anything like that? All right, now I was figuring you would, and Tyler, there's stuff in there, if you can look through it, I think you have things there. I want to mention something about,
The Bode plot questions in the whole.
yes, I was going to get to that right now. I was hoping somebody would mention it. Yeah, Bode plot is something that's so important, but I don't know how often it's covered.
It was just a little weird finding the expressions for them.
That's normal.
Oh,
Which one do you want to take a look at? We can all take a look, because this is something you're going to be asked. There, now I said it. So, if you were going to, which one do you want to take a look at? Do you know?
I don't have.
He does. Did y'all do them? A lot of times people don't do things until like Thursday night, and they try to cram. Some of this stuff's going to really overwhelm you in the next couple weeks, especially the microwave stuff. If you don't keep up day to day, you're probably going to be lost because you won't know what to ask. Which problem? Okay, stop there. That one. All right. Is this asking for a function that can do it?
Yeah, so it starts on the y-axis at negative 12 dB.
Here? Or here?
Up there, like, or that's where it like starts, and then it goes.
Is it 12 or negative?
Negative 12.
Okay, go ahead.
And then it goes down at negative 20 dB per decade.
That's common.
To 3 on the frequency axis.
And is this, what frequency is this?
It's omega. Is that what you're asking?
Yeah, no, what value right here?
That's 1.
1.
This is omega, not F? Okay.
Yeah.
So this is 1, and this is
3.
3?
Mm-hmm.
Okay.
And then it goes to 0 dB to omega equal to 10, and then it goes down at negative 20 dB per decade. Again.
All right. When you're doing something like this, the first thing you have to understand what's being plotted. And here is frequency, but the paper takes the longer. This isn't a very good Bode plot. This is supposed to be a flat line, and these points should match these points. So they give you information. When it comes in at 1, it's already coming down to 20 dB per decade. So I want to talk about first, what does the 20 dB per decade pertain to, and how do you figure it out? I want to do this first, start there, and then I'm going to show you how to get 40 dB per decade, how to get 80 dB or 60 dB, either increase or decrease, right? Here's where it comes from. If you have any function A, we'll put it a simple pole, over S plus 1. Now we know S is equal to J omega, right? Better yet, let's plot S. Let me make it AS plus 1. This will be easier for you to understand. So I have some function, and there's a coefficient on S. Well, actually, I'm not sure how you were taught this stuff. Tell you what, I think I know the way. They always had just S alone when you were taught this in signals and systems. So let me go back. Forgive me. I'm going to have over S plus A. Let's just leave it there, okay? Now S is J omega. Does everybody understand this? I prefer to use S because it's all inclusive. I can have a complex pole there. I can have sigma plus J omega, so I'm going to leave it as S. This is a functional form. It could be for anything. It could be a transfer function. Suppose we call it a transfer function of S. All right. Now if we're going to plot that on a Bode plot that you've heard before, what we end up doing is taking 20, if this is a transfer function for voltage or current, 20 times the log, that's a base 10 log, of the absolute value of A over S plus A. Right? And we say that's going to be H, but now it's going to be in dB. Are you all with me? Remember, if it's a transfer function for voltage and current, it's 20 log. If it was power, it would be 10 log. Follow me on this, guys? So when we have this, if you have a log, you can break it up. Log A times log B is log A minus log B. So I can say this is really 20 times the log of A minus, and that would be 20 times the log of S plus A. Now, I didn't put the absolute value here, but you should do that too. You all agree with me? Okay, we're going to start when omega is very small. I'm going to plot this over here. This is going to be versus omega. All right, when effectively S is 0 or omega is 0, start there if you want. You with me, class? If it's 0, then I can say H of S equals 0 would be equal to, and this is in dB, would be 20 times the log of capital A over small a. I just combined and put S. Do y'all agree with that? Now, I don't know what that value is, but if you give me a capital A and a small a where the pole is, I can tell you. Everybody understand that? That's where you start this thing. So down here, and we can put 0 here. That's where it starts, whatever that is. 20 times the log of magnitude of A over small a. Any value could be. Capital A could be larger or smaller than small a. It doesn't matter. This always works. Now it's going to stay that way, and hear me, until all of a sudden S has the same value as A, or J omega's magnitude is A, or omega equals A. Does everybody follow me on that, class? So mark that point. Here it's going to be omega is equal to A. You could put S equals A and S is J omega. Either one is acceptable. It would be a magnitude. So it's omega equals A. You follow me? Now at that point, you see that minus sign? Once we start increasing, this term will start becoming dominant, and it will start causing it to go down. So it'll go flat here, and this is the first break point, and it'll start going down, and the rate is minus 20 dB per decade. Let me explain why, in case you haven't been shown. Just write that down. How many remember Bodie? Usually people have some rust. I hate to say it. Every time I've given them simple Bodie problems, some people in the class, yes,
If it's coming in from,
should be flat.
okay, so that's why you had to make it flat, because if it was coming in,
It's constant until S becomes comparable to A. See, until this pole, see, as long as S is much, much less than A, then this is basically capital A over small a.
okay,
As soon as S becomes comparable, when S's magnitude is equal to A, then this becomes the square root of 2. And if you take 20 times the log of square root of 2, you get 3 dB. And you're going to be down. So this is really called a 3 dB point. You can put that down there, but it's not essential. Now it starts going down to 20 dB per decade. Here's how I know it's 20 dB per decade. This is a great question people are afraid to ask. Take a look at this. When S equals A, it's really minus 20 times the log of, and now it's going to be square root of 2 times A. Well, 20 times the log of square root of 2 is 3 dB. It's 3 dB less than it was back here. But we don't show that curve like this. What we do is put a dot there, and we know this is an approximation. So it's going to start coming down at 20 dB per decade. All right, when S is equal to A, right, you're going to get a certain, well, better yet, let me just do it this way. If I take 20 times the log of 10, I get 20. 20 times the log of, make it 100, that's 1 decade difference in the argument. Well, the log of 100 is 2, so this would be 40, right? I've gone over a decade in magnitude, and when S is greater than A, you really just look at the magnitude of S. You follow me on this? So here I've gone up exactly 1 decade, from a 10 to 100, correct, class? That would be a decade, factor of 10. And I go from 20 to 40, or it's minus 20 dB per difference. If there's a minus sign in front of it, it's going down, minus 20 dB per decade. If it was in front, it would be going up. Do y'all follow me? Just follow me. So it would look like this. That's a simple pole. Got me on this, class? Everybody good with that? Now, the next thing I have to mention is, what if you have this argument? I bet you most of you see this. So I'm just trying to show you how to sketch these things based on the pole zero constellation, really, when you break them up. Suppose I have this. You tell me what changes. Well, I still have to take the log of it, right? So I'm going to take, when I take 20 times the log, this would be the Bode plot of A. I can break that out, right? And in case somebody doesn't know, if I take log of capital A times capital B, that's the log of A plus the log of B. Does everybody know that? Right? And if it was log of A divided by B, it would be log of A minus log B. Okay? Just making sure. Believe it or not, there's sometimes these little gaps you're afraid to ask about. And I'm trying to fill in anything you don't understand about this. You good with this, everyone? All right. Now, it's going to be 20 times the log A. That's the first part. Then minus 20 times the log of, we can put magnitude of S plus A squared. Now, here I got to make sure you know this. You all agree with what I've done? All right. Well, if I have something x to the n, and I take log base 10 of that, that's equal to n log of x. Everybody follow me on that? The exponent comes out in front. How many remember this stuff? I hope everybody does. If you don't, just, I catch myself all the time wondering, wait, something about it. Something I haven't used in a while, crazy Bessel function argument that I should know. And so don't be afraid or ashamed if you don't remember everything. So what can happen here when I have the log of S plus A squared, it comes out in front. Follow me? Y'all with me on that? So I can just make this 40. Are you with me? I could have put on n there as a superscript, right? And I would bring on an n times 20. But I'm just showing you, because this is a common thing. Going up and down 40 dB per decade or 20 dB per decade is very common. The key thing is finding out when that kicks in, and it always kicks in. Now remember, I didn't put a coefficient of S here. It always kicks in when the S argument is equal to the pole value. Are you with me? Everybody? So now let's go to this one. This is kind of a classic. We're trying to create an equation that dictates or depicts this. Any questions about what I've shown so far? Okay. Now, with this one, you see how they don't really show you anything flat there. Follow me? You just see it coming in at minus 20 dB per decade. What that means is you have 1 over S by itself. You don't know where the pole is. Just put 1 over S. So you have 1 over S. That takes care of this. It's going down at 20 dB per decade, right? At this point, we want the thing to start increasing at 20 dB per decade to cancel off this decrease. Y'all follow me? I'm going to stop. And again, thank you for scribing this information, because I got to say this, I look at these notes and I wish I could write them. Okay? So, now what is it going to be? Times S plus, what would I add to that? 3. Just 3. You all see that? That's where it starts going up. So S plus 3. All right, it's going to stay there until S or omega is 10. Leave it in terms of S though, because S is J omega. So then we have over S plus 10. Now that takes care of the shape, right? Everybody agree? How do we take care of this constant where it starts anyway? What would you do? Nobody wants to seem like a smarty. You just multiply by a constant, right? You calculate that constant in a second. So you multiply this whole thing by k. And that is going to depict that function. Now we have to calculate the value of k. You all agree with that? Just making sure, but whenever I see heads bowed and writing, I'm trying to teach myself, back off for a second. Let everybody get done. All right. Now, I'm going to take the Bode plot of this, so I take 20, right, times the log of this. And that's going to be the Bode plot. And here it's going to be 20 times the log, base 10, of k by itself, right? Then I'm going to have minus 20 times the log of simply 1 over s. What's that fall? Minus 20 times the log of 1 over, of just, there should be just s, not that. Minus 20 times the log of s plus 10. And then it's going to be plus 20 times the log. And here it's going to be magnitude of s plus 3. Are you with me, everyone? Now what we have to do is this. We have to figure out the value of k. Well, we know when s is 1, or omega is 1, it's minus 12. Correct, class? So we come over here and we make this minus 12. This is when s is equal to 1, correct? All right, so what is the log of 1? 0, isn't it, class? Everybody hear me? Log of 1 is 0, right? Log of 10 would be 1, log of 20 would be 2. What's the log of 0? Minus infinity, yeah. All right, it's tending towards negative infinity, correct, class? That's the thing, keep in the back of your mind. So this one goes away. Log of 1 is 0. This one also goes away because s itself is much less, right? But there's a problem, isn't there? I wanted to make sure I do this. What's the problem? But there's still a 10, isn't there, class? So just follow me on this. This one goes away. But this one, we have to leave that as 10. You all follow me? There's two ways to do this. This is the way I'm showing you requires you add the constants here. So there's a log of 10 here, isn't there? What about here? When s is 0, s is 1, we still ignore this value. Right, there's still a 3 though. You all follow me? We got s is 1. 1 compared to 3 is much less, so we ignore the imaginary term, the j3, and we just put s equals 3. And all that is equal to minus 12. Correct? Here's where people mess up right here, by the way. They forget those terms. Now there's another way to do it. If I would just put the coefficient here as 1 and put s over that constant, divide top and bottom, I get rid of it. I'm doing it this way because this is the way you saw it, I think, in signals and systems. Right? All right, now, what happens? What is the log? Let's do it this way. I got minus 12, right? Equals 20 times the log of k, right? And then it's going to be what? Minus 20 times the log of 10. What is the log of 10? 1, so it's just minus 20. And then it's going to be, I put that down right. And then I've got log of 3. Check that out. Log of 3 times 20, right there. And I think that's 60, or 3 dB. Check it out. No, wait a second. No, it isn't. Okay, log. What did you get for that?
9.54.
Yeah. So this is minus, or plus, sorry, 9.54. And now if we wanted to solve for k, what would we do? I would take this and this, take it to the other side, right? So I add 20, right? And then I'd subtract 9.54, right? And now I have that, right? What is that number, by the way? 20 minus 12 minus 9.54.
Minus 1.54.
Minus 1 point what?
54.
And that's equal to 20, right? times the log of k. So then we divide by 20, take it to the power of 10. So I have 10 to the minus the quantity 1.54 over 20 is equal to k, and you can tell me what that is.
0.84.
Now, is that the equation he has?
Yeah, he just had 0.8, and so I must have dropped.
All right, I took it out another decimal place, or maybe I rounded. Y'all follow me what I'm doing, class? That's how you do this for any of these things. And I'll tell you one thing about Bode plots. As an engineer, I'm speaking from my experience, you see these all the time. You'll see them in amplifier design, antenna performance. You'll see them in data analysis, where they talk about the overall performance of a certain algorithm versus the amount of information gap. Something like, you're going to see it in everything. Machine learning, you can't avoid this type of thing, Bode plots. And remember, they're an approximation, not exact, but it's typically the way everything's done. I'm glad you asked. Is there another one you want to see?
Oh no, I think that I got the gist of it.
I gave you another one, right? Which, how about we try, just because I'm a little suspicious. I've had every time people get casual and think they understand, I'm a little suspicious about this. I can come up with one. Let me see, Jack. Yeah, that one. That one. Okay. So this is the one that you're going to see at S or omega, really, this one. And this one does this. No, it's not exactly that. And how far down does it go? Below this point? Or?
It goes below it, and then it goes to 20, that like where it goes flat is at 25 dB on the
25 is omega, right?
well, omega is
Oh.
30, and then it's 25 dB magnitude.
What's the peak here?
It does not specify.
What is this, 20?
Yeah, 20, and then minus 20 on the other side.
What's the frequency it comes in at?
It does not specify. At the peak is where it turns is 10. That omega is equal to 10 at the peak.
What's this?
30.
Okay. That's flat here. Am I at 25?
Yeah.
All right. Let me show you how to do this. Because this is a good one, right? We know basically what's going to happen. I have something increasing at 20 dB per decade from the get-go, so that's just S on top, right? When it hits this point, that pole, it starts decreasing at 20, so I have to subtract 40 dB from that, correct? The rate of increase. Then it flattens out here, which means there's another pole at 30 that is going to what? It would be on top. It would actually be an increase of, and it would start at 30, correct, class? Everybody with me? So if you do this, the general form would be some unknown constant k. Now that one's going up, so it's times S right off the bat, right? Then we have S what? Plus 10 squared, right? If it was just S plus 10, it would level it out. We're going up to 20 dB. This would take us down to 0 dB increase. And if I put a square there, now it's going down to 20 dB. You all follow me on what I'm saying? What else?
There's an S plus 30 in the numerator.
All right. Now, that's the general form, right? I know I'm going to take 20 times the log of that. Do you agree? But I want to show you something. So when I take 20 times the log of this, I end up getting 20 times the log of k plus 20 times the log here And then I have an equation where I basically have S times S plus 30 over S plus 10 squared. Did y'all follow me in that class? Yep.
Why is the S in the numerator again?
Remember, it came in, it was going up at 20 dB per decade. That means it's got an S in the numerator.
Okay.
All right, because does everybody follow me on this class? Make sure you understand the reasons why I'm doing things. Now, if it was going down at 20 dB per decade from the beginning, be in the bottom, it'd be 1 over S.
All right.
Everybody got that? All right, keep going on this one. I need to get this thing equated to this. Boy, there's a lot of ways. I got a value here, right? I want you to take note of this. Does that value change at all? Let's assume it's the same that S goes to infinity, right? Well, as S goes to infinity, what happens to this term? I have S squared on top, and I have S squared on the bottom, plus other terms, right? The squared terms will dominate. Do you all agree with that? So this is really going to be 1 over 1, isn't it? So 20 times the log of 1 as S goes to infinity would be 0. Do you all agree with that? So really, the log of k here, 20 times the log of k, I can equate to 25, can't I? You all follow me? You follow me? I'm going to make sure.
You're not good.
All right, so that means I'd simply set 25 equal to 20 times the log of the magnitude of k. And I get what? 10 to the 25 over 20 is equal to k. Correct, class? And what is that value? It's greater than 1, right? I can't look to tell. If it was 10 to the 1, it'd be 10.
I got 17.7.
Is that what the book has?
Yeah.
Thank you. Well, y'all follow me on that, class? That's about 17.7. And that's how you do these things. And here's where you get into trouble. Just one last tip. Here's what people will do. They'll spend a lot of time trying to figure out what that point is right there. Or what this point is right here. Right? What my advice is, if you're going to figure this thing out, look at the extremes. Either as S is just as low as it can go or as high. And if it plateaus like this, then you got it. Just let S go to infinity if it's up here and you got a value. And if it's down here and you got a value, just plateau it, let S go as low as possible to 0. Got me on this, class? That's how you do these problems. I hope this helped a little bit with your bodies. Now I asked you a few things about the values of inductors, capacitors, I think and resistors, correct? From a plot. And the whole idea is just knowing how to get the plots for the different elements. Is there a specific question about that you want to ask about it now? Anybody? How about this? I'll make it as fair as possible. Look over this stuff. Consider that a question about Bode plots is coming on Friday. All right, fair enough? Considering it has to do with either an inductor, a resistor, or a capacitor, where I give you a drawing and you tell me what the values are. Follow me on this, class? And we can go through each and every one, but I think I gave you it for homework, didn't I?
Mm-hmm. Yeah, you gave us one where.
I think I gave you more than one. Or I gave you resistors.
Yeah, it was a
Yeah,
resistor.
that's fine. But any of them are easy. And if you don't remember, a resistor looks like a resistor, then it doesn't, starts falling off, it hits a relative minimum at the resonant frequency, then it starts going up, right? If it was an inductor in the beginning, well, it looks like an inductor, right? With really small resistance possibly. But if it's just coming in, it's going up at 20 dB per decade, hits self-resonance, starts coming down at 20 dB per decade, correct? You can get that one easy too. And for a capacitor, it's what? The opposite. It comes in at infinity, starts going down 20 dB per decade, hits a self-resonant, goes up to 20 dB per decade, right? And that's it in a nutshell. Maybe I can give you some more. Anyway, that's what I really wanted. I wanted to make sure we're clear on that. Go ahead.
So if an inductor hits self-resonance, does that mean that it's its parasitic capacitance is equal to its inductance?
Not
Or-
capacitive, it's reactance. Capacitive reactance equals inductive reactance, exactly.
So that, it just looks like a resistor then,
Well, yeah,
right?
yes and no. It doesn't have any imaginary component, but the value may be much different than the actual value of just the resistance. Because remember, as you go up in frequency, the skin depth goes down. So it's not just the DC resistance. So you've got to be kind of careful about that. All right, and I'm not going to give you any higher order problems. It'll be straightforward. All right, class? All right. Maybe we should do one just to make sure everybody's on the same page before I move on. I'm skittish about this because when I teach EMC, I have students that really don't understand Bode plots, and I'm assuming they do, and there's this huge disconnect, but hopefully you got the Bode plots. So now we're going to take a look at figuring out values for a resistor. We're going to have a simple resistor like this, R. We know R itself, right, has some lead inductance, Lx, right? And this is going to, actually, tell you what, let's do a capacitor now that I think about it, because that one's the one, this will be a capacitor. For C, we start out with a capacitor, then you have a resistance that's Rx, and you have an inductance that's Lx, a lead inductance, right? Are you with me? This would be the impedance, Z. Are you all with me on this class? We're just assuming, this is a capacitor model, first order, correct, that I gave you? All right, now put in the impedances. Well, for a capacitor, the impedance is 1 over Cs. For a resistor, it's just the resistance, and for an inductor, it's SLX, correct? It would be S times the inductor. It's like J omega L. Do you all agree with me? That would be the impedance. So now when I take a look at this, I have Zn, and I'm going to take it right to a Bode plot. So 20, or I'm just going to put Zn in dB would be equal to 20 times the log base 10 of the quantity 1 over Cs plus R plus SL. And I'm going to drop the X subscripts. We know that's it. You agree with that, class? Everybody with me? This is a simple capacitor. Now if you look at this right here, probably the best thing to do, even though you don't have to, is get a common denominator. And so I'm going to multiply everything, let's see. Going to be 1 plus S times R times C plus S squared LC. And it's 20 times the log of that over that's it. So the only thing I've done is got a common denominator for one reason. When I take a look at this, there's two things I'm going to tell you can get from this right away. I know when the thing is at self-resonance that this term right here will cancel that term, but we can go ahead and do it. So if we have something where what this will look like for a capacitor, you can see this just by looking at this. This S is small, it's coming in as a 1 over S term. You all see that? If S is very small, make it 0. It's going to infinity, the 1 over 0, right? So it's a 1 over S pole here. Here it's even more obvious. I put an S here. It's coming in. So we know it's doing this. self-resonant frequency. I'm putting it in terms of omega. You would divide this by 2 pi if you wanted it in terms of F. And then it's going to go up. You all agree with that? Can you all see it in the back and thing? With me? And everybody agree with that? So if we're going to get this thing, the one thing, if we want values, I'm going to have to give you something, but first I'm going to show you how to get it. Well, this is the thing that's interesting right here. That's where the self-resonant frequency occurs. At that frequency, the capacitive impedance or reactance here will equal the inductive reactance here at self-resonance. And therefore, at self-resonance, 20 times the log of R will be the value here. So if this value right here is K, I can set it equal to 20 times the log right there of R. Y'all follow me on that? Remember this one thing, the key to this thing is understanding when you're at resonance, the inductive reactance, the capacitive reactance is equal to the inductive reactance. They cancel. If it was in parallel, all right, they would still cancel. You understand? With me on that? All right, now, when I have that, I can easily find K, right? Because, if I can find R, just take K divided by 20 and take it to the power 10, right? Now, here's the thing. If I give you a self-resonance in L, you have to be able to find C from this frequency. Do y'all follow me? So if I give you any two of the three of this portion, you get the other one from what's left over. Do y'all follow me in this class? All right. So that's sort of how to do it. For inductor and capacitor, it's the same thing, but I even graphed that out where the cut frequencies are and everything, so you can take a look at your notes on that. All right. Now, next. I want to mention something. Dr. Wentworth's book talks about signal grounds and shielding. You've had to deal with grounds when you were in Dr. Wentworth's, well, in the laboratories, right? What is a ground in your own words? Anybody? What is it?
Reference to
It's what we're going to always measure things with respect to. That's the definition of a ground that electrical and computer engineering people use. And it's usually a voltage, right? It's almost always a voltage. So when we have something at ground, we know any other voltage measurement in that circuit with respect to ground, we usually take a lead and clamp it to the ground, and then we just have one probe and we measure the other voltages. That's normal. That's a signal ground. And it's also a chassis ground. Now a chassis is just a metal box that contains a device. It's all a chassis. A signal ground can be on a single board. It has a ground point, just a breadboard. A chassis ground, if you had 20 boards on there, a chassis ground would be the metal enclosure held at 0 and everything measured with respect to that. They don't have to be the same. They're close, but they don't have to be the same because as current comes through the wires that connect the signal ground to the chassis ground, there's a voltage drop, so you can get millivolts of difference between the two, and that's important with microelectronic circuitry. Also, there's something called an earth ground. How many have heard the term earth ground? Earth ground is very, very important when it comes to wiring high power things, and generally your house wiring. Normally speaking, the power company, when it sends power, it sends it with 3 phases, and it really has 3 energized lines, but it doesn't have a ground line. The ground is the earth. I don't know if you're taught that with Dr. Gross's course. The earth is the ground for that thing. Now that's ground for power company. When you have one phase, I think it's 7,200 volts, comes off of a pole and it's stepped down at plus or minus 220 before it comes to a resonance. Isn't that, Dr. Gross would teach you that, right? When that comes in, the plus or minus 120 is with respect to an earth ground. And the way you get an earth ground, and I'm not an expert in this, so if there's an electrician in here and you want to correct me, you can tell me the truth. But the idea is you buy a long grounding rod and you put it in earth deep. And then if you've got a problem with a lot of I don't know, quartz or granite or something in the area, and you're worried if that's really going to be a good ground, you can sprinkle copper sulfate or rock salt in there, let it seep down. It'll make the ground more conducting around. What it effectively is then, if you measure the resistance from that point with a meter, and I don't even know what the standard is, it might be 10 meters away where you put it, just a short probe in there, it's got to have a resistance less than a certain value in order for it to be an effective ground rod. And I don't know the requirements for the second one. When I teach this, you got to understand, Europe, Asia, Australia, they all have different standards. So you got to look at the laws that pertain to your locale. And I'm sure residentials are much different than businesses. So just realize there's all sorts of laws that dictates what is a grounding rod. Nevertheless, the grounding rod is there for a couple of reasons. One is protection. If lightning hits your structure, you want to have some way, shape, or form for any place in the exterior of your house or anything like this, if it's lightning protected. It can short that thing right to ground without going through your TV set or something else and blowing it up. Has anybody ever had a device destroyed by a lightning strike in here? Well, I've got stories about this. My wife, before she was my wife, was living in an apartment complex, and she had one of these TVs with a cable that was connected from the wall, and I think it was just like Spectrum or Charter. And anyway, lightning hit the building, and it blew her TV out. I mean, the electronics were fried. Another person I know had lightning hit back in the day when they had just, do you ever remember the day or see these antennas that are just like wrapped? They had antennas that would be on the roof, VHF and UHF hit the antenna. Antenna was connected to the TV, and it blew the TV apart. From what I understand, I wasn't there for this. You know what ball lightning is? Has anybody ever heard of it?
UFOs.
Huh?
UFOs, right?
No, nothing to do with UFOs. Ball lightning is something that occurs. It's very rare, but it does occur. Submariners had the most common, the old World War II submarines, when they went from diesel to battery and then from battery to diesel, and they broke the circuit. There's a tremendous amount of current going through something that has a relatively high inductance. Now, anytime you try to separate current from a large inductor, what you get is an arc over. Have you ever heard of that or seen it? Dr. Gross has some great videos on this. Well, that arc over at times can try to be stopped, and what will happen is you get a plasma ball. It's this plasma instability. I'm not sure if it's the Bennett-Pinch instability, but it's one of these things. And what will happen is the currents will circulate in this ball in a way that confines the actual energy, so it can't get out, or confines the current, and it'll just kind of hum and stuff like this. It's rare, but it does happen, and they've documented it all over. It happened the most common time was in submarines, when they go from like running diesel engines to from batteries to diesel engines, and they broke that kind of circuit. They'd see these huge flashes and ball lightning until they put a safety resistor in there that would short it out. Anyway, that's an interesting story. Well, lightning needs a way to go down the ground, and that's what a ground rod provides you. It also provides you protection from the ground. Now, did Dr. Gross go through safety ground and why it's important? How many know that? What's the big deal with safety ground? Well, so you can't be the ground. If you have a safety ground on your system, right, it's that green wire. If I'm holding this and the floor is earth ground, right, and for whatever reason there's something that broke off and I'm touching the hot line, it won't go through me, it'll go through the actually, you couldn't touch the hot line directly, but you would actually have the thing short through the internal ground. There's more to this, but that's basically what a ground is for safety and for measurement, for ease of use. That's what it is. So in grounds, Dr. Wentworth shows you different types of ground structure on page 521. I don't quiz you on this. This is the signal ground. That's what it looks like. That just means on a simple board, it's the zero potential. This is a chassis ground. And this is an earth ground. And these are shown on page 521. That's basically what the deal is. Here's the problem, and I don't give you, I'm never going to ask you a problem that deals with this directly. But if you have 3 boards, we're going to talk about ground loops in a second too. All right. Each one of these things has a wire, and this is going to be your chassis ground. All right. So this is from a signal ground here, signal ground here, and signal ground here. And if each one of these has 3 milliamps of current, then from this point where they connect to the actual chassis ground, there's going to be a total of 6 milliamps, and this wire will have some resistance, so there will be a voltage drop there. This wire will have some resistance, so there will be a voltage drop here, and this potential, even though it's small, will be different than this potential because this wire is longer, will be different than this potential. That's the difference. You can have a whole bunch of small variations in the chassis ground, in the signal ground, but the actual chassis ground will be the same. Now, chassis grounds are used a lot of times to make sure that you have some common way for current to get out that's not going to go through a path that's somewhat dangerous. That's another thing. But chassis grounds just mean that. They're the chassis of the device. From a chassis ground to an earth ground, it depends on the application. But generally speaking, is the chassis ground would be going through the shortest possible length of wire to get to the earth ground. Now I've got to show you a few things that cause problems. Dr. Wentworth shows you a couple of them about how to connect the ground. And this is on 522, and I'll show you the real reason that it's so important to connect these things correctly, especially with high power applications or very high frequency. He shows you something he's not talking really about AC effects, but this is important. And I can tell you this from experience. When we were flying this railgun, we had hundreds of kiloamps of peak current, and the wires were jumping across first just because of the electromagnetic forces. And I learned a lot about the importance of making sure you don't have ground loops the hard way. Anyway, so if you have, say, a unit like this, nice long unit, and say you want to connect it here, you want to put a ground here to, say, make this a chassis ground. And you also want to ground it here because, just to be on the safe side, and say this is the floor. Now I want you to follow me on this so you can understand this. I grounded this thing at 2 points. It doesn't matter really the scale of this thing's not important. But I'm not worried about the current from this thing getting off. What if I have currents that are in the radial direction? That happens all the time, by the way, with lightning. Lightning hits the ground. There's currents going out radially, and in the old days when golfers used metal cleats, if their feet had a different radial distance to the point of contact, the current would go up one leg, down the other, and knock them out. Lee Trevino's a famous golfer, got knocked out by something like that. And now I think it's all rubber, and they close the golf courses when lightning is within 25 miles, I think. But I don't know all the facts these days. I know one thing, if you're ever in a boat, if you can see visible lightning, as soon as it happens, start counting. And you can figure out, you know how fast sound travels. If you get to less than 15 before you hear thunder, leave. And that's just a rule of thumb. If I hear thunder and I'm on the water, like Lake Martin, worse yet, Lake Erie, I get out of there. I get out of the way of it because it can kill you, and it does kill people. So for this, here's the problem. Current here can be going out radially, and it'll go up that way and down this way. Unintentionally, this whole thing would be infected. So what you should do is only ground it at 1 point. That's the point. That's the thing. Here's another thing that happens, and this is far more trouble. All right? And this is important. Suppose I have something, all right, where I have current where I have a magnetic field caused by, say, a generator, anything with a lot of current, elevator motors, they draw a lot of current, there's a magnetic field, it's time varying. Well, if there's a B field penetrating that, just look, here's a loop, isn't there, class? You know the integral of B dot ds is the flux, and the time rate of change of the flux would be the induced voltage. Y'all follow me on this? So if you ground anything at 2 points, what happens is you open yourself up for this thing acting as a single coil and inducing EMF in this thing. And these things can be serious if you got a high power current or if lightning hits nearby. Lightning's really the bad one. Follow me? So the moral of the story is grounded at 1 point. And you don't have any problems with chassis grounds. And they should, if you go from any kind of a unit to another ground, either from chassis to earth or from signal to chassis, go through one path only. Follow me on that? Now, usually you don't have, honestly, most of the time these days, if you're working in a plant, Boeing or something like this, and you're doing something where they're using a lot of electromagnetic energy, say it's a railgun or something like this, they'll have resident electricians to take care of that for you most of the time. You're not required to, but you gotta be understanding in small company, God help you. Because small companies, you are the jack of all trades that ends up doing 90% of everything from a YouTube video. And if you get the wrong YouTube video, I'm not kidding about this either. I don't know if you know this in the real world, but YouTube is like a godsend for a lot of people in small companies, the people that are just hacks. You can kill yourself, especially with electricity. So be careful. I gotta get out of here. I got a class. I'm gonna cover shields next time. You already know what your quiz is on.